so I'm going to present Concordium's consensus design to you today with a little bit of detail about the implementation, but it's really most about what is the design principle behind what we have been building and what a lot of you guys are actually implementing. So just to remind you, and you all know this, I mean, this is kind of the stack we have in Concordium. We have a peer-to-peer layer. On top of that is the consensus layer. That's what I'll be talking about today. And then there's a lot of cool stuff on top of it. There's a transaction layer, identity layer, smart contracts. We'll probably do MPC at some point. And then all the cool applications up here. We're doing formal verification of all of it in the long run. And we're also looking at incentives and governance, right? But I'm just going to assume that all of you have a pretty rough picture of what this is and really kind of in a nerded way zoom in on the consensus layer today. Really just talk about why does it look like it does. So just very roughly before we go, I'll just touch briefly on the peer-to-peer layer, just so you know how I'm thinking about it. And this is like just at a cartoon level, right? So what we have is a peer-to-peer layer where we can send messages. It's built such that each of these nodes is connected to some random subsets of all the other nodes on the network to make it robust. This ensures that if you want to send a message, you can do it even if 80% of the network is controlled by some corrupted parties that try to bring it down. And we all know how it works. You send your message somewhere, and then you inject it into one machine here. Then it will send it on to all its neighbors. That one will send it on to all its neighbors, and so on. And even in presence of a lot of corrupted parties, the message will find a way to spread across the network. That's the basic starting point of a blockchain. Now, that's very nice, and we would almost be done if there wasn't this tiny problem that if you send two messages at the same time, they will reach different nodes at different times. So some people will see the red node there first, and some will see the green message here first. And that means as it spreads on, we'll have a situation where some saw red, then green, where some others saw green, then red. Right? This could be a problem. I mean, if the green message is I transfer 100 kroners to Lars, and the other one is I transfer 100 kroners to Anders, and there's only 100 kroners on my account, the last message have to be rejected, right? And then it's pretty important which of the two messages was the last one, right? So we need to be able to decide on what's the order of these messages. That's a seemingly tiny problem, but yet the topic of the next more than 1 hour. So the way it works in Nakamoto-style consensus protocols is there's a distributed lottery. So there's just some way that some node here in the network can discover that it won the lottery. And this is something it can prove to the rest of the world. So what you win when you win the lottery, besides maybe some coins, is the right to order the outstanding transactions. So since this one here was the winner, which saw green then red, it will probably tell the rest over here to reorder the messages, and then they should consider green having arrived before red. So that's the basic idea in Nakamoto-style consensus. Someone can win a lottery, and then they tell the rest of the network to reorder the outstanding transactions. This establishes a global ledger, and on top of that, you can then build a lot of cool stuff. You can build your bank, you can keep track of where containers are, and so on and so on. Okay. So that was the basic idea in Bitcoin. I mean, to do the consensus like this is pretty robust. It works even if people come and go because the lottery is robust. And what we have been working on in Concordium then is to take these initial designs, the Bitcoin Ethereum designs, and improve them to make them faster and to make them more secure. I'm going to talk about 4 aspects that we've been doing research and implementation on. One is efficiency by using proof of stake. We've been working on throughput via something called sharding. We've been working quite a lot on confirmation time via something called finalization. And then we've been working at different other aspects of making it both faster and more secure at the same time, for example, by using dynamic block time. And I'll try to dive a little bit into each of these and tell you about why we have designed it as we did, and also some of the stuff that's upcoming for the development teams. So I'm going to dive into these 4 topics now and tell you a little bit about why the design looks as it does. Okay? But before that, just one slide to explain the one design principle that's behind our design. So this is a quote by singer-songwriter Graham Nash. It says, "Life is not perfect. It never will be. You just have to make the very best of it. And you have to open your heart to what the world can show you. And sometimes it's terrifying, and sometimes it's incredibly beautiful. And I'll take both, thanks." Now, if it's not completely obvious what this has to do with blockchains, I hope it is when we reach the last slide. But this here is the design principle. So let's try to take and make this here a little bit more nerdy. It's also a nice motivational quote. So let me try to first dive into energy efficiency. What we've been doing here is applying a proof of stake lottery to be much more efficient than designs like, for example, Bitcoin. So first, a little bit about the lottery. I mean, for the lottery to work, we need it obviously to be decentralized. If it's just one server in the basement somewhere saying who won the lottery, that server can take over the entire network by saying, I won, I won, I won, and then start censoring the network. So we need the lottery to be completely distributed so that anyone that wants to participate in the lottery can just say, I'm part of the lottery, and then have a chance to win the lottery. It also turns out, and I'll talk much more about that, we need that mostly honest nodes are winning the lottery. Otherwise, again, I mean, the corrupted nodes can create more chaos than I mean, the honest parties will be able to create order. So how did Bitcoin do it? So this is the claim to fame of Bitcoin, that they actually found, I mean, the designers found a way to do a distributed lottery that kind of works. Okay, so we all know that the way it works in Bitcoin is there is some kind of puzzle. It's P, it's just a random number. And the way you win the lottery is you try many times to apply a so-called cryptographic hash function. That's just a function that takes an input and gives a deterministic output. And you try to give it an input X so it hits this P, okay? This puzzle. And that's just the way you go for it. And if you try it on one input and it doesn't hit, you try it again. And that's why, I mean, if you want to win the lottery, people are just buying a lot of computing power to keep, evaluating on a lot of X's to try to hit this P here. And that works. Anyone can sit and do this. And if we believe most of the computing power in the world is honest, this will mostly have honest users, and that's very good. The only problem, of course, is that when you win the lottery, you also get like a Bitcoin, or a fraction of a Bitcoin, which by now is worth a lot of money, right? So if such a thing is worth 200,000 Danish kroners, it's worth for you to spend 199,000 Danish kroner in electricity to win the lottery, right? So this is a terrible design. I mean, if the price of Bitcoin goes up, people just buy more computing power to turn the value that they get for solving this lottery thing here into electricity and heat. So it's the world's biggest radiator, right? And that's to some extent, like the most stupid design you could come up with, right? The more valuable the system becomes, the more people will take electricity and turn it into heat. Well, it was just meant as a feasibility result, I think. I mean, it was not meant to actually reach the scale it did, because this would be a really stupid design, right? So how do we do this better? Well, one of the techniques that's out there and that we are also working with and improving is called proof of stake. So instead of having, one clock cycle being a ticket, it's $1 is a ticket. So in a proof of stake system, you will have accounts. Let's give them a name, account A. On the account, there is some kind of balance, B, that's how much money is on your account. And now, every second will then run a lottery. Okay? So every second, let's give them a name. Let's just say second number 7 since we started the blockchain. And the way the lottery is run is just as follows. So you take the same hash function here as before. You hash, as it's called, the name of the second and the name of your account. That gives a random number, and that's kind of how lucky you were in the lottery. The one with the biggest number will win the lottery. And then to make sure that, mostly honest party win, we scale it with how much money you have in the system. The idea being, if you have a lot of money stored in a bank, you tend to have less interest in burning down the bank. Right? So we have the people that actually have a lot of money in the blockchain win the lottery more often, and then we hope that ensures that mostly honest people are winning this lottery. So you get a random number here, scaled by how much money you have in the system, and if that is harder than some kind of threshold, we say you won the lottery. That's all there is to it. It's really not rocket science. And then you can just take Bitcoin, and then you replace the lottery with this thing. Now you have a proof of stake blockchain. What's the difference? If we compare this, let's say that we, in the Concordium network, at some point get to a scale where we have 100,000 nodes. That will take us a while. There's no other blockchain out there with that kind of number of nodes in the world. Well, how much computing power would it take to run this lottery? So remember that every second you have to compute one of these hashes and then compare whether it's bigger than some number, right? So if there's 100,000 nodes, each of them is doing this every second, that is 100,000 hash function evaluations per second. This is how many times Bitcoin is doing it per second, okay? You don't even know the name of this thing, right? So if you look at just the order of magnitudes of efficiency improvement by running a proof of stake thing compared to running, a Bitcoin design, you cannot even count the number of zeros here before I'm on the next slide, right? So this means this notion that blockchain somehow is energy inefficient is completely scratched. 100,000 hash function evaluations per second. My cell phone can do that without losing power, basically, right? So you can take the whole thing and run it on a cell phone. And there's a lot of sending messages around still and stuff like that. But the idea that blockchains are burning energy is gone scratched. We solved that. Then, for the connoisseurs out there, you actually do more. Instead of just hashing the second and the address name, we actually put a signature in between here. That is mostly something that has to do with protecting against denial of service attacks, so other people cannot see whether you won the lottery before you did it and therefore start attacking you. But besides that, basically what you're just doing is replacing the lottery in Bitcoin by hashing the second and the name and the account name. To see how lucky you were. Okay, so that solves the energy efficiency problem. Check. Then I would like to talk something about confirmation time by adding what's called a finality layer, which we are the first blockchain to solve. And therefore, the next 15 minutes or so are going to be with some visible pride. Here we have a really nice feature. And what this thing is about, it's how fast can you trust the transaction that you put on the blockchain? And just to see why there would at all be a problem with that, we have to dive much more into how this lottery thing is actually helping us agree on what the transactions are. Okay, so remember, the way a blockchain works is somewhere in the world, someone wins the lottery and gets to send out what's called the next block. So a block is just something where, there are some transactions in it, and then there is a certificate proving that the one that built the block actually had the right to build this block. So when we have a new winner over here, what this party there will do, what that node will do, is send out a new transaction saying first green, then red. Here's my proof that I won the lottery, and then it points back here to what it considers the previous block. And that's just to order all the transactions in the system. So it now means that if you are looking at what are the transactions in the system here, it would be 1, 2, 3, 4. Okay. So you just point, where am I adding these transactions here? That's very nice. These things are called blocks. The pointers then makes it a chain, and now we have a blockchain. Okay. That's really cool. We would be done if it would just remain a blockchain. But the problem is, unfortunate things can happen. For example, the lottery is completely distributed. People are just sitting locally and seeing if they won. So sometimes it happens that two nodes win the lottery at the same time. Okay? And then they send out both of them a new block, And then it will look like this. The one builds there and the other one builds there. They don't have time to see each other's block before they extend the chain. So now it's not a block chain, but a block tree. That's unfortunate, because we would like to have one truth. I mean, what's the order of transactions now? Is it 1, 2, 3, 4, 5, 6, or is it 1, 2, 3, 4, 5, 6? I mean, the idea in Bitcoin was then to say, I mean, we resolve this by just relying on luck. The rule is when you win and get to extend the chain, you have to extend what you consider the longest chain. And if you have two that's equally long, just the one you saw first, some kind of tie-breaking rule. So there will be some kind of forking going on because of this. But we have this general rule about extending the longest chain, which will resolve it. So at some point, someone wins and extends there. And now the rule is just, now this is the truth, okay? So it means if you ask what are the transactions in the system, it would then be 5, 6, 7, 8, and this stuff never happened. Okay? So you just ignore it. That's of course annoying if this here was a transaction that where someone transferred you 100 million to buy a rare Lamborghini. You gave him the keys, he drove away, and now the payment is gone. Right? And up here he transferred it to another guy, so the account is empty. Okay. Well, maybe it doesn't happen too often, right? It gets worse than this. Another way it could happen is there could be some of the nodes in the system that's actually interested in this happening. Say the guy that paid you for the Lamborghini. So if he's controlling some of the nodes in the network, he can do this naughty thing that say he wins the next two nodes. If he controls 10% of the stake, this will happen with probability 1%, which is already bad enough. And then he could add both of them like this. So he extends on the shortest chain. So now the truth is, if someone would ask you what's the stake in this system here, it would be 5, 6, 7, 8, 9, 10. And this stuff never happened. Okay? But he can keep doing this. So if there's a lot of corrupted parties in the system, next time they could add it here. And then if it wins two more, it could add them here. So you could get longer and longer, stuff that you thought was the truth that just disappears under you. Money you thought you had, stuff that already went up to higher level applications that just appear under you. And it's more or less impossible to code anything on top of this. And even if you think most of the time it doesn't happen, if there's a chance it happens, and you want to build a high, like a really critical application on top of it, you have to handle it. And that's kind of the worst case. You have to sit and program a lot of stuff for events that never happen, right? It's completely impossible to program on top of such a thing in a reasonable way. Okay. So forking also happens because of malicious behavior. And very simplified, one can show that, the possible rollback lengths, what's the longest chain that could suddenly disappear from my view of what is the truth, is proportional to something like how slow is the peer-to-peer network compared to how fast you produce blocks, times the fraction of corruption. And the reason why the slowness of the peer-to-peer network matters is, remember what was dangerous if you had two honest winners like here, that didn't have time to see each other's block, then they extend and create a tree. And that means you should create blocks much, much slower than you can propagate them. So you build in a chain and not on the same thing. So slow peer-to-peer networks are dangerous and corrupted parties are dangerous. And in particular, combination of them is very dangerous. So this gives us this problem of when do I trust a transaction? Let's say someone paid me here for my car, and I wonder when should I give him my keys, right? So if your blockchain is looking like this here, it's after a few blocks appeared. I say you look 2 blocks back and you say, probably this one is good now. You give him his key and he drives away. But that could also be that we are in a high corruption, slow peer-to-peer network setting because, for example, the peer-to-peer network is being slowed down by a denial of service attack. And then the situation could be looking like this here instead. And this means, we have 2 competing chains, one here and one here. And it's not completely sure which one of these 2 is going to win in the end. That means if you're going to hand out the keys to your car, you better make sure that you're paid all the way down here. Now, if this here was Bitcoin, for example, and each block takes 10 minutes, you have to look far back. And as a cryptographer, with small probability, something we would typically say 2 to the minus 60. And if half of the network is controlled by an adversary, that means you should look at least 60 blocks back to be secure on Bitcoin. 60 times, well, that's something like 10 hours, right? It's a long time. It's a long time to stand there with the keys. It's even longer if you just bought some peanuts in a shop, right? So, and even, I mean, I would even say, even looking far enough back is never a solution, because you never fully know whether you looked far enough back. And that means ultimately, if you're building a critical application, you need to handle that exceptional day where you get a rollback that was longer than you expected, or your whole thing would crash down, right? If you build your application like that and it's a critical application, there will be an investor that says, this line in the code here where it just says everything just crashes, what's that about, right? So it's not good enough. It's good enough for like a toy situation like that Bitcoin was meant for, but it's not good enough for building anything like real-life high-stake applications. So what can we do about it? So it looks like if we pick, some cutoff point and say, you know what, I look this far back, and I consider everything that's behind this point here, I consider that safe, right? Then sometimes, in this case here, it could actually fail because one of these here is eventually going to disappear, right? I could also choose to look very, very, very far back. And then it would take a month for stuff to be final in my world, right? And then probably it never happens that you get a rollback that long. But in this kind of Nakamoto-style consensus, you need to pick one of these. Either you look very, very far back, and it's very slow to get a transaction considered final, or you look back very short, like 6 blocks or something silly, right? And then you run a real risk that someday you'll get a rollback that long. But you have to pick, right? So you have to pick either fast finality or high assurance. There's no way to get both of them. You need to look some number of blocks back. Now, a recurrent design principle we have is whenever the world imposes on you to pick between two things, like either fast finality or high assurance, and it looks like you cannot have both, we will say, I'll take both, thank you. Okay, so let's try to now make a design where we get both of them. Okay, we'll want to have fast finality and high assurance. Okay, how do we do that? The way we do it, ignore the code. But the way we do it is we're going to run a fairly simple procedure which we call finality. Let me do it in pictures instead. So the way it works is we're going to have, for the blockchain, since the last was going to be a finalized block, let's say the last one was down here, there will be a deterministically picked committee, or rather, it's a committee everyone knows who is. And they're going to run a good old, what's called Pft Consensus Algorithm. This is stuff we have known since the 80s. This is the kind of stuff you did if you had like 3 databases running to have replication, and one of them crashed. You would like to know which one of them is the truth. Right? So what these algorithms would do is now and then the databases could run a Pft algorithm. Each of them report what is my view at the truth. And then you run an algorithm, and if they all agree, it will come out and say, check, you agree, and then you know what the state should be. And if there's a disagreement, it will come out and say, you disagree. This is an oversimplification. That's basically what it does. It checks whether you agree on a value. And you will all end up agreeing on whether you agreed or not. So what do they do? I mean, these will just be bakers that have this special role of being on the committee. So what they will do is they will pick some height. Let's say height 1,000. It was just agreed that the next place to do finalization would be at height 1,000 in the tree. So what they do is when they reach height 1,001, when what they consider the best chain has length 1,001, they will look 1 block back and then vote on what they see. So that means, for example, if they are sitting like this here, I mean, this guy would vote for that, this one will vote for that, this one for that. So they're voting for 2 different values, so the algorithm would fail, and they'll all learn you don't look at the same thing when you look one back. Then they do it at height 2. So they try to finalize the same height, 1,000. Now they just wait until they're at height 1,002. They look 2 back and vote for what they're seeing. Again, they disagree on what they're looking at. And then they do what's called a binary search. Now they do it at height 4, 8, 16, 32, and so on. And already at height 4, we see that if they look 1, 2, 3, 4 back, they all see the same value. So the Pft algorithm is going to come out with, you agree on what you're looking at. So now, since they all agree on what they're looking at, they know what they agree on, and that is now considered a final node. They'll all sign off on that. Everyone knows who the committee is. So they will get all these signatures and see, oh, the committee is signing off of this thing. So it's now, by every baker in the network, considered a final node. And then, bam, you just scratch everything that's not behind it. So everything that's behind the final node is considered final. And everything that branched off it will just be erased. Okay? And that means that could be a bad thing. I mean, if my car was paid here, that's annoying. But at least I knew that it was not final yet. That's the important thing here. You know when something can disappear, maybe, and when it can't. And you know now exactly, if you were paid here, you can now hand over the keys to your car, and the money will never go away, because it's just by algorithm illegal to ever roll back behind this thing. This is just defined to be final. And that's what gives you finality. Okay? Now you know that this part of the tree will never disappear. I mean, non-final stuff, you can still use it if you're buying peanuts or swiping money to a friend that you know where you can swipe them again by. But if you're really handing over the keys to your Lamborghini to a guy that doesn't tell you what his name is and wearing a mask, you wait for it to be final. So that's what it's giving you. You can do high-risk applications in this kind of thing. What's really cool about this now is you're getting both of them now, right? You have, like, with finalization will happen in best case, right? So most of the time there is not really a lot of branching. So already when something is like 2 or 3 blocks deep, and right now on the testnet it's typically just 1 deep, it will finalize, right? So that means within 1 block you know it can never go away again. Whereas if you're doing an ad hoc thing, you would have to wait like 60 blocks and still run a risk that it might go away again. So in that case, you have a worst case, waiting time for finalization, right? So this gives you a better guarantee and is faster, right? So it was not true that we had to choose between either, fast finalization or high assurance, right? No, we'll take both, thank you. So that is cool, but we can use it for even more. So that solves 2 problems for now. We can do stuff energy efficiently, and we can have fast confirmation time. Let's try to be even better, because it turns out that finalization as a tool will allow us to do a lot of new things that previous blockchains couldn't do. I would like to just try to dive into one thing that's called dynamic block time and see what we can do there. So as I talked about, and that's why I actually really needed to tell you about this lottery, right? We saw that the speed at which you're producing blocks is critical for your security. If you're producing blocks faster than they can propagate on the peer-to-peer network, you'll tend to get branching, and then you'll tend to not grow a chain, and ultimately you can get so much chaos that you're actually not growing a chain, and that you never get finality. So you should take some time in between the blocks, and that's also why the lottery need to be non-manipulatable. I mean, you should not just be able to raise your hand and say, I would like to win. It needs to be hard so you can space out the winning events. Okay? And then there's, of course, a design choice now, right? You can either do like Bitcoin and say, I produce a new block every 10 minutes. So that means there would be snugly hiding in there in the corner if we're looking at blocks per second, right? Or you can be much more aggressive like Ethereum did, right? And produce blocks much, much faster. I mean, a little bit polemically, right? I mean, Ethereum is basically Bitcoin where they just reduced the block time. And then they added some JavaScript. I mean, that's polemic, but not far from the truth, right? So they just said, no, we just produce blocks faster, right? Let's hope it's not too fast, because we know if we produce blocks too fast, the network is not secure, right? And now we know that the security is dropping. I mean, the faster you produce blocks, I mean, the further you move out here, your security will be dropping. And the formulas tell us that it's dropping kind of exponentially. As you approach the propagation time, if you produce blocks faster than they can propagate, you have no security. So you're hitting it out there. And it gets bad already if you get close, right? You should be like 10 times as slow as they can propagate to have some kind of nice security if you want to do the analysis. So you have to hide snugly in here. So you have to try to sneak out here, try to be fast, produce blocks often, but not get to this point here, right? The problem is that this curve here depends on the peer-to-peer propagation time, right? Because it's relative. Your block time should be slow relative to the speed of the peer-to-peer network. So if you get an attack on the peer-to-peer network, if you get a distributed denial-of-service attack slowing down all the nodes so they get a lot of crap input so they cannot propagate the real blocks, the curve will look like this here instead. Right? So under a not very complicated, attack, you will have Ethereum out here in the insecure range, and Bitcoin still is snugly hiding in there in the corner. Or maybe I'm wrong. Maybe we can build peer-to-peer networks that can just never be attacked by a distributed denial-of-service attack, though I doubt it, right? And Ethereum did a stupid choice, right? They should have gone out here, produced blocks much faster than they do already, right? Even though it's already quite aggressive. Importantly, this asks a question to anyone designing a blockchain, and I am. So what should the block time be, right? Should we do 1 block per 10 minutes, or should we do 1 block per second? Right? So I'm going to do a cliffhanger there. Either we have to, pick very quickly, making blocks, and then being possibly insecure, or do it very slowly and being secure, right? There's a choice to be made. Should we be fast, or should we be secure? So I'll do it by asking a leading question. So let's say that instead of building a blockchain, we were building the next car of the future. It's electric, it's self-driving, and all kind of stuff. And your brilliant CTO is done designing the car, and then he comes and says, hey, CEO, I have this one hard design question left. How fast should the car drive? I need to put in one number, of course. Should my car drive 200 kilometers an hour or 2 kilometers an hour? Because we did some analysis, and it turns out that sometimes, like even 2 kilometers an hour is a bit fast. And sometimes when you are on an empty German Autobahn, 200 kilometers an hour is not even enough. But what number should I pick, right? So, as a CEO answering your CTO to this question, what's the obvious answer? Anyone from the audience? You're fired. Get out of the room, right? You put a speeder in the car, right? You put this thing in the car that allows to adjust the speed to the driving conditions. Isn't that smart? Let's do the same for a blockchain. Okay. So let's not put in a block time. Let's do blocks as fast as we can in the current driving conditions. It's going to be a bit simplified now, but what we can do, for example, is to say, hey, presto, we had this way of doing finalization, and as part of that, we were looking some distance back. So these people were looking back here. And they know they were looking back when they finalized last time, okay? Now looking back shows there was some kind of branching going on. So that means there's some kind of behavior like this going on in the network. And in general, if they're on a chain, they only have to look 1 back to agree. So it will definitely finalize with delta equal 1. So by looking at this value here, when they finalized, they get a measure of how healthy the blockchain is. So we'll just have to take that as a measure of what are the current driving conditions. If we're producing blocks too fast, delta will grow. If we're doing it too slow, it will drop to 1, right? Maybe we want to be aggressive and put of the place where most of the time it's 1, but now and then we do a tiny branch, because then we're just at the edge of the speed at which we can pump blocks out. A simple way to do it, and it's more complicated than this, but one simple way to do it would simply be to take the lottery from before and then scale the hardness with delta here. This thing will work. It means that if I'm producing blocks too fast, delta will go up, then the hardness will go up, and then the block production rate will go down because it's harder to win the lottery. So that's a negative feedback, right? It means if you're going too fast, you get slowed down. So this just have a natural equilibrium somewhere. Then you can put in a constant if you want, but this will stabilize your chain somewhere. And that's kind of what there is to it, except for 50, 100 pages of scientific proofs and stuff to make it actually work. But that's kind of the main idea. So you get a feedback that if you go too fast, it gives you a feedback so you can slow down again. And then be producing blocks almost as fast as you can in a healthy way. And I mean, we have seen that we can already produce blocks faster than any other blockchain with this thing, because we can allow ourselves to go as fast as the driving conditions allow us, and not as fast as is, safe in any possible driving conditions, right? Because that is really slow. So this gives us a lot of speed. So the question is how often to make a block? I mean, it's just as fast as you can. So we designed a blockchain where we're out here. We're really producing blocks really fast. If someone attacks our peer-to-peer network and the security curve moves there, we just slide behind it. If then they get angry that they couldn't break it and launch a massive distributed denial of service attack and put the security curve in there, we'll just slide behind it, right? And then when they get tired of using their resources and just slowing down the chain instead of breaking it, the attack goes away. There. We just slide out there again and we start having a throughput again. So we'll have to sometimes slow down. That's clear. I mean, if they stop the peer-to-peer network, you can't do anything. It's clear that the speed have to go down, right? The best you can do is slow down to the speed that's safe, and then when the attack is not there, slide up again. So again, I'll take both, thank you. I mean, we can build a blockchain which, in good conditions, when life is giving you beautiful things, you're just pumping out blocks, several blocks per second, and when it's giving you ugliness, I mean, you just cope with it, and you slide back. You produce blocks slower, but you stay safe. So that means Concordium have the first ever Nakamoto-style consensus blockchain that can actually do this. It's what's called partially synchronous. It means it doesn't need to make an assumption on how fast blocks propagate. We just assume that they propagate with some speed, and then we adjust to whatever reality is thrown at us. So yeah, that means at the end we can get a blockchain that is more secure, because it's secure in all network conditions, and at the same time faster. Because whenever there is fair weather conditions, you're pumping out several blocks per second. I mean, that's really cool that you can at the same time be faster and more secure, right? With a very, very simple trick. There's other kind of blockchains out there also having finalization. And what I would like to do now is dive a little bit into why are we doing this two-layer design, okay? Why do we have a Nakamoto-style blockchain and then with finality on top? Because there are other blockchains out there, for example, Algorand, which are what's called pure Pft blockchains, Byzantine fault-tolerant blockchains. So what they do instead is they don't have a Nakamoto-style blockchain underlying. Instead, they have a committee where they vote on each block. They vote on this one. When it's went through, they wait until there is a new block and they vote on it and so on. And then they just build a chain where every block is final. I mean, isn't that better? I mean, why all this complication with two layers? And since I know that our developers went through quite some pain to implement a two-layered approach, let me try to dive into and telling you why did we put you through that. Okay, so why do we have a two-layer approach? So what we did instead, right, just to remind you, I mean, what I just talked about is we had this tree thing where we then have a finality layer that's kind of now and then running a BFT thing on top. And one of the design criteria, one of the design ideas is already visible here. These BFT things, they're slow. So we know that to run one of these BFT algorithms where you agree on an input, you need to use at least 2 or 3 rounds of communication. Everyone talking to everyone in maybe a 1,000 party network. That is just slow. That's going to put a significant cap on how fast you can push blocks out. You need 3 rounds of everyone talking to everyone. That means the blocks you can vote on will be spaced out a lot. Now, if you have an underlying Nakamoto-style blockchain, that's really not a problem because in the time in between you can finalize, you're still pumping blocks out. So maybe you can produce 100 blocks in the tree and then just have the finality layer only finalize every 100 blocks. I mean, if you can measure, I mean, this is an engineering task, right? You measure finalization takes a minute. I have a block time of 1 second. Then you just finalize every 60 blocks. But you're still putting out blocks in between that. And that means you can put out much more data. You're basically virtually putting out the biggest block you can in between 2 finalization points. And that means you can get much faster, you can get much better throughput. So you're having throughput while this slow BFT thing is trying to actually finalize a block. So that's the first thing. I mean, you can, with a 2-layer design, get high throughput and this at the same time as fast as possible finalization. Finalization can be as fast as the blockchain is in any kind of BFT design like Algorand. But you get data out all the time nonetheless. And if you're paying for peanuts in the shop, you might not even need to wait for that to finalize. So just when the block comes out, you can walk on because they know who you are. You swipe the credit card. We have other ways to check people that cheat, right? If you've paid a friend in a bar, it's enough that it appears in the next block. If it somehow rolls back, you just tell him next day, you know, the beer you paid me, it went away, could you do it again? And he does it again, right? So it means it's also useful to have non-finalized blocks. Often, I mean, you can, based on the circumstances, pick whether you want to trust it or not. So it's cool to have blocks coming out all the time and not just as slow as a BFT design can do it. Another reason to have a 2-level design is to treat what's called the Cap Theorem. So if you ever took a course in distributed systems, the first thing they do to you is the Cap Theorem. It means consistency, availability, partition. And it basically says if a network partitions, you cannot have consistency and availability at the same time. So what it means, just to illustrate, I mean, let's say, you know, the network partitions and it's impossible for 10 minutes to send messages between the old world and the new world. Some fool dug over the transatlantic cables and the network and the internet dies, right? Or what happened in Latin America that, you know, there's a power takeoff of a huge region, right? That brings cuts the internet, right? These things happen. Now and then, it's seldom, but they happen, right? Now, clearly, let's say we have some kind of, I have 100 kroners on my account, and then I try to take one here. I try to take 100 out of an ATM. And over here, I have some conspirator that also tries to take 100 kroner out of an ATM, right? What should the ATM do, right? Either it says, you know, even though I cannot communicate with Europe, I'm going to give these 100 kroners to the guy, right? In this case, you don't have consistency because then the account will be negative afterwards, because if that's the algorithm, it will also happen in Europe. Now I withdraw 200 kroners and there was only 100 kroner on the account, right? So you cannot have a consistent system if it's cut. So what you have to do is just not hand out money. You just bring the entire system down and say, oh, we're not handing out money because I don't know if someone in Europe is trying to get the same money out. And then you lost availability. And you have to pick. You can prove that pretty broadly and in great abstraction, which academics like. I mean, for reasonable the definitions of availability and consistency, you just can't get both of them. That's clear, right? It's a triviality, right? I'll take both things. So let's first look at what are blockchains doing. I mean, what the different blockchains out there doing, Nakamoto style versus kind of the BFT kind of thing. So what is Nakamoto blockchains doing in case of a partitioning? Well, people will keep winning the lottery on both sides of the cut, maybe slower, but people will keep winning the lottery. So you'll be building 2 blockchains. one on one side of the cord and another one on the other side. So the blockchain remains available. You can get money out, you can make transfers. At some point, this cut of the network will go away again, messages can pass again. These two chains meet, the longest one wins and the short one goes away. So everything that ever happened over here in the US for a while just goes away, okay? Good for the guy that got out 100 kroners, right? And now it didn't get deducted from his account. So they chose availability. What does BFT designs do? Well, they choose consistency, because it's a voting kind of thing. They need everyone on the committee to sign on the block, or 2/3. And now if the network, partitions, clearly you cannot have 2/3 of the committee on one side and on the other side. Even if some of them are corrupted and play a double role, even if 1/3 of them is playing a double role, you cannot have 2/3 plus 1 on both sides. So they have chosen that. The blockchain will just stop. If the network segments, BFT designs just stop. They don't produce blocks anymore. Money are not coming out. You don't see anything. That's a little bit of a problem if you if you want to buy peanuts in a shop or swipe 100 kroners to a friend. So what is a two-layer design doing? It's kind of getting both of them at the same time. So what would happen to our design if the network partitions? Well, for a while, the underlying Nakamoto-style blockchain is still growing on both sides, right? But the committee is split, so they cannot vote, so finality stops up here, right? So they will still see the blockchain growing, but then for a long time, they will see that stuff is not finalizing. This is cool now. This is a feature now, right? Finality stops because you can't get it. We know we cannot get availability and consistency at the same time. The chain keeps growing, so you have availability. You can still trust a payment where you swipe a friend 100 kroners in a bar, you buy peanuts in a shop, right? But you know something is abreast, you know something is wrong, so you're not going to hand out your keys to the Lamborghini to a shady guy until you see stuff finalizing again. And then when a longest chain grows, the partitioning goes away, finality comes back, the alternative history goes away, and now you can hand out the cars. So you can get both of them. At least you don't have to, as every other blockchain did until today, pick in the design which one you want. You don't have to say, my blockchain has availability, my blockchain has consistency. You can have the chooser pick it, right? The chooser can, during the period of of a partitioning, just say, yeah, no, it's not final, but I'm paying a friend, I can get the money tomorrow. So you pick availability dynamically. And if you're handing out the keys to the car to a shady guy, you wait for finality, right? So you can do it dynamically in the moment. And in that sense, get both of them. We know you can't get both of them, but I can cheat and put a kind of. So you can do it. Basically, you can dynamically pick availability and consistency with this kind of design. And that is really cool. And we're the first blockchain that can do that. I'm not going to stop. Why a two-layer design? There's a number there's a number more reasons. And one thing is to cheat this thing here that we're also very proud of, which is called the 33% corruption versus finality dichotomy. Let me explain that. That's a little bit complicated, but let me explain it. So what it's about is the following. If you look at the BFT kind of designs, like Algorand, they can actually fork. So it's not completely true that they can never fork if they're a pure proof of stake. There can be situations where, for example, you have more than 33% corruption, or where you have very fast-moving stake and participation, where in face of actually a partitioning, you actually have a committee on both sides that manages to finalize a block. And since this is not supposed to happen, when it happens, these things are broken forever. Okay? So for example, if you get more than 33% corruption, and this thing here happens, it's broken forever. So BFT's designs in that sense is they're extremely fragile. This just have to happen once. Nakamoto-style blockchains, on the other hand, they are really never fully broken. even if you get 75% corruption and the network is messing up everything for a while, I mean, you have something like this happening in two chains growing at basically the same speed, but at some point, one of them will become the longest one and the other one will roll back, like this. So what Nakamoto-style blockchains need is 51% honesty over long enough periods. It doesn't matter that there is more corruption than 50% for a while. If it then just drops down and on average you're good, you're below 50% corruption. This is two very, very, very different things. Right? It means one kind of design, the BFT kind of design, have to stay below 33% forever. Whereas the other thing has to stay below 51% over long enough periods. That is, I mean, two different worlds. So if you have something like this, if this curve here is the corruption, here the BFT things like Algorand will break. Whereas if you have a Nakamoto-style blockchain, even if you get very high corruption, at some point it comes down here and it recovers again and becomes a blockchain again. Okay, so that's one really good reason to like kind of the Nakamoto-style consensus algorithms. But if there's anyone in the audience that were alive in the 80s, some of you were, I can see that, no insults. Then you did, theoretical distributed systems, you'll say, wait, I mean, you claim you have a blockchain with finality, and you claim that you can tolerate more than 51% corruption. This cannot be. And this is what, I mean, the point I was getting at. You can actually prove that if you have a blockchain that can tolerate more than 33% corruption, it cannot have finality. So this thing of breaking at 33% in BFT designs is because they finalize every block. And if they do that, they have just bought the sour pill that they have to break at that point because they insist on finality. So there's no way to keep finality running. But what we can do, and we have a design for that, this is very much a work in progress, but it's like at TRL1 now, we know it can be done, there's going to be quite some details, is what we can do is we can have this finality layer running whenever it's possible. Whenever corruption is below 33%, the finality layer is running, it's been good, these periods here. Then when finality, when corruption hits 33% here, and where probably you cannot have finality anymore, it will turn off. But then underlying Nakamoto-style blockchain is still running. You still have a blockchain. It means you can recover, even if corruption comes all the way down here, at some point the Nakamoto-style blockchain will recover. And then you can use that to, at some point, respawn the finality layer. And then when you're below 33% again, you get finality back again. So again, it's the same thing. I will take both, thank you. Someone told us we have to pick between, tolerating at most 33% corruption or have finality. No, I'll just take both, thank you. I'll have finality when it's possible. And when we probably know we can't have it, we'll just not have it. But it doesn't mean we have to explode at this point, right? Like BFT designs, like Algorand do. I mean, you don't have to have the whole thing blow up, right? You just find a way to recover, turn off finality, and then recover when the weather is good again. Is that now the 5th time I said I'll take both, thank you? You see, there's a recurrent kind of thought here. It's just make sure all the time you get the best you can. And if someone tells you have to pick between A and B, you just take both of them. So it's a very greedy kind of design. So with a Nakamoto-style blockchain plus finality layer, you can actually, to some extent, tolerate both 49% corruption and have finality, even though it ought to be impossible. Last thing is throughput, where we're looking at sharding. So there's this inherent inefficiency in blockchains, where if you have 1,000 miners, right, they all have to run every contract. If you have 6,000 miners, all 6,000 have to run the contract. That will just cost 6,000 times as much electricity as running them on one machine. There's no way around that, right? You have 6,000 machines doing the same thing, that's going to cost you some electricity. And then there's a lot of communication and lotteries and blah, blah, blah. Well, that is like the inherent inefficiency. And you don't want 6,000 of them. There's this thing here going on. In general, as you get more nodes in a network, security will grow and efficiency will drop. But security will grow something like this here. It will level out at some point. After a few thousand nodes, you really don't need more of them. So as you add more nodes, you just get more and more inefficient, but you don't really get more secure anymore. If you have too few, if you have like 60 nodes or 2 nodes or 3 nodes, you're not secure, right? So there's also a lower limit, right, on how many nodes you want in your network. So I mean, because of this inefficiency thing, you have to pick again, right? Either you pick a big network and you're slow, or you pick a small network and you're very, very efficient, right? I mean, for sure this time you have to pick, right? So which one should I pick? Fast or secure? I'm going to trust the audience this time. Yes, I'll take both, thank you. So let's see how we do that. So what you do is sharding. The first idea is sharding. So what you do is, if you have like, let's say, 6,000 nodes, you're not going to run one blockchain like up here with 6,000 nodes. You're going to break it into 100 blockchains with 60 nodes in each, for example. Okay? Now we have 100 blockchains. There's 2 effects on efficiency here. Each of them is smaller, so it will actually be faster, let's say 10 times faster. And you have 100 blockchains, right? Each of them 10 times faster, so the overall speed up ideally is by a factor 1,000. That's quite something, right? You're using the same resources, but you're putting 1,000 times more transactions through per second. So that's the base idea. Well, then we should be, but wait. We can tolerate 1/3 corruption, right? Now, if you have 60 in each shard, 33% of 60, that's 20. So now it would only take 20 bad nodes out of 6,000 to break the system. Is that what you're designing? Because that's really bad, right? I mean, for sure there will be someone that will be able to add 20 bad nodes. Well, not completely, and we'll now get into probably the most complicated part of this thing here. We'll do something, we'll add just another layer. Whenever you're stuck, just add another layer, right? We're going to have something here that's called the control chain. And on top of it, it will be running a lot of these shards here. Each of these will be very, very efficient and therefore potentially insecure. But we'll have the control chain underlying here, which will be very secure and slow, but kind of hedging the security. So the way it works is as follows. So the control chain, the big one down here, that will be implemented by all parties, say 6,000 nodes, using the design I already showed you. All the bells and whistles, partial synchrony, finality, So this will be extremely secure. It will be slow, but it will be very secure. But because it's slow, I mean, we'll just make sure it doesn't handle too much data. So we just make sure it only handles a little bit of control data, few transactions per second. And then what it will do, it will take the 6,000 nodes and then randomly assign them into shards. 16 each. And then it will help these shards with finalization. So they don't have to finalize themselves. It will take care of them. Basically what they'll do is just post back on the control chain when they finalize a block. So they don't have to be secure enough to finalize. They will use the underlying very secure control chain for that. And then it's all these shards up here that will do the actual transaction. So if we zoom in a little bit, it will look like this. We'll have a very slow control chain here, not handling very much traffic. It's just talking to the shards. And then it's the shards here that's taking the bulk of all the transactions and then talking, via the peer-to-peer network. This one is very slow, but handle little data. These are very fast and handle a lot of data. So there's a number of design principles in play here. First of all, we took the control chain and implemented by this very, very secure 6,000 nodes thing I already showed you. That's obvious. That's a no-brainer, right? Because this one is like the key part of the design. So just make it as secure as you can. Okay. Design principle 1. Now this thing is slow. And as I said, we can handle that and just make sure it doesn't have to handle a lot of transactions, right? It's just, keeping track of, are these shards alive, basically. That handles, that gives us security and speed at the same time by having then delegated to the shards. And then an important thing is we have these shards here. We have the control chain do the finalization. And that means the control chain needs to stay below this 1/3 corruption, otherwise it can't finalize. But the shards not. Each of the shards is just going to be a Nakamoto-style blockchain. So they can tolerate to just stay below 49% corruption over long enough time. Right? So they don't have to actually be that secure. And therefore, we can make them smaller. So we can make them size 60 or something like that. So what we will assume now is we have a population of nodes out of which we assume 2/3 of them are good. And then I sample a little subset of them and make that a shard, and I just need that half of those are good, right? That sounds feasible, right? If I have let's say 3,000 nodes, 2,000 of them are good, it should be possible to make a random sample and then get something where most of them are good, right? You start with 2/3, you should not just be unlucky and drop below 1/2. And that's why we can get smaller shards, right? We allow the threshold to go down by saying the shard is not supposed to do finalization. So I can sample from a lot of good and just get a little bit of good, and that should allow us to get a reasonable shard size. Did I lose? No. There is a problem with that. No. So the intuition is wrong here. So here's a puzzle. So let's say you do that. You have, let's say, 30,000 nodes. 20,000 of them are good. Okay, 2/3 of them are good. Now you sample at random m of them. And you want to have a good guarantee that at least half of the ones you sampled are good. And let's say small. We say with good probability means except with some very small number. This is what cryptographers consider small, 10 to the minus 180, for example. It means even if you do it all the time, which you sample shards all the time, for 100 years, it will never happen. Okay? How many should you sample for this to behave? Anyone would care to give a guess? Anyone know what that is? It's a guy thinking, but it's a particular guy. Do you know what that thing is? Yeah, that's Jesper being beaten by Deep Blue. Anyone remember the year that happened? 1979. So that's the shard size you need. That was the hint. So you need to sample close to 2,000 nodes to be sure that with good probability all of them are good, right? So that means we came from a shard size of 6,000 down to 2, and we sampled right from 6,000, and now we have a shard size of 2,000. I mean, that is certainly not going to be worth the effort, right? I mean, that's a huge shard size. It's kind of mind-boggling that this is what you need, but thanks to Christian, I know it's correct. No, he did the computation yesterday. I mean, if it's not correct, you're in trouble. You have to redo the entire talk. Oh, it's correct. I checked in. But we can handle this. So let's take another look at these 49. So we need at most 49% corruption in these shards. It turns out that it's 49 is not 49. So it turns out that, security in general for blockchain means it's live and safe. Live means it's actually doing something. It's putting out blocks. Safe means that the parties in the shard are agreeing on what the blocks are. That's the safe part, okay? It has to do something, and people have to agree. And the real restriction is that if you have something that's live against L% corruption and safe against S% corruption, the sum of these have to stay below 100. Now, of course, that then means, right, if you really insist, as most blockchains do, that they're the same, they both have to be like 49%, right? So you just pick one of them and say, if the corruption is below 49%, my blockchain is doing something and it's doing the right thing, right? But we can be smarter than that. We can, for example, just imagine, for example, in the committee, we say everyone have to sign off on the block. Okay? So let's say we add a mechanism like that, and now and then the committee, now and then the blockchain, every miner in the shard have to sign off on something and then play it back on the control chain, right? Or 99% of them, right? Then we would now have a blockchain that's secure if just 99%, I mean, if you have at most 2%, 1% corruption, let's say. Right? But it will also very, very easily deadlock, right? Let's say 3% of the nodes crashes. Now you can never get 98% signatures, and it just stops, right? But that might not be a problem. So we do that. So we start up in an initial situation. We start up with a shard size of, let's say, 60, but then we insist on having safety 98%. So it means if up to 98% of the nodes are corrupted, that's all but one, my blockchain is still safe. And we do that simply by saying everyone has to sign off on the block to finalize it. And now if a single one of them crashes, the chain will deadlock. But since it's the control chain that's doing finalization for us, since we're reporting back to the control chain to finalize, the control chain will notice this. It sees a shard that stops having a heartbeat. At some point, for several minutes, it's not finalizing anymore. Then it will kill it, and then it will spin it up again with a bigger size. So there's some kind of corruption going on. So for example, it could then spin it up with, say, liveness 10%. I can tolerate 10% crashes and 89% corruption. That will give a larger shard size, 221. This one Christian didn't do. I did this one, so that's probably wrong, but we'll get it right before we implement it. And then even if 10% of those are kind of corrupted, if there's actually a bad attack going on where 10% of the network is corrupted, I mean, you could just take the full step up and say, now, I mean, fuck it. I just spin it up with 4949. Go to full size, one full shard size. We are under attack, so we slide back in a safe situation, right? But you bring yourself into a position where when things go wrong, it's only the liveness. You never do something wrong. And liveness you can monitor. We have the control chain, which is very secure. And then you just bring the shard down, bring it up again, right? So I think that's, I mean, if we just zoom very, very quickly in on one shard, then it will look like this. The shard here is handling the bulk of the transactions, goes directly to the peer-to-peer layer. There's a launch thing here that launches the shard with size, let's say, 60 to begin with. Then there's a thing here we call finalization as a service. That's doing the finalization. And then there's a kill process here that's monitoring finalization here, how often it's happening. If it stops, it will kill the shard there, and then it will just get relaunched from this one, but with being bigger. So sorry to the development team, but there will be quite some complexity coming to you over the next year or so with these things. This is still at TRL 1 or 2. So you can again say, I'll take both, thank you. Distribution costs you to be slow, but you don't have to be at full distribution all the time. When the weather is good, you can run with small shards. So that was maybe, I don't know, was that the 6th time or so, and then I think I'm done. Brings us back to the overarching design principle. It says, the network is not perfect. It never will be. You just have to make the very best of it, and you have to open your tech and your science to what the network can show you. And sometimes it's terrifying, and sometimes it's incredibly beautiful, and I'll take both, thanks. And that's a citation by the Concordium tech and science teams. And that's all I wanted to say.